Right, I hope you got the hard copy of the study pack of the mass spectrometry. In fact, in the last session, we discussed about the IR spectroscopy, and this is mass spectrometry, right? The basics of the mass spectrometer we have discussed under the Unit 1 of the AS, and this is advanced mass spectrometry. In fact, as to the new syllabus, this section on the mass spectrometry is included in the new syllabus AS, even though this was there in the old syllabus under A2. So please note that this is a part of the AS now in the new syllabus. Let me first brief you on why we have this spectrometry, mass spectroscopy. As I mentioned last week, there's a difference between the spectrometry and spectroscopy. As for spectroscopy, that is a study of the interaction of the electromagnetic radiation with matter. So we do observations based on how electromagnetic radiation interacts with the matter, and observations are made and molecules are identified. So that's why we say IR spectroscopy, right? It's wrong to say IR spectrometry. That is wrong. Likewise, it's wrong to say mass spectroscopy. Rather, you should say mass spectrometry, because spectrometry, there is no interaction of the IR radiation. Only in spectroscopy, there is no interaction of the electromagnetic radiation. It can be IR, it can be UV radiation, it can be NMR, radio waves. So those electromagnetic radiation, if it interacts with the matter, we use the term spectroscopy. As for spectrometry, there is no such electromagnetic radiation involved in the technique. So it's wrong to say mass spectroscopy. So it's mass spectrometry. So in spectrometry, there is no interaction of the electromagnetic radiation. Now, let me just brief you on how the mass spectrometer works. In fact, we have discussed the same on the AS earlier. In 1818, F.W. Aston invented this mass spectrometer. The purpose of the invention at that point was to identify the relative atomic mass of the atoms and molecules, and to identify the number of isotopes. Of course, now the mass spectrometer is widely used in various other, research. For example, like space research, they use mass spectrometer to identify the elements present in a sample of rock, which is brought from different planets. And then you can also use mass spectrometer in the pharmaceutical industry to analyze the purity of a drug and to find the presence of various elements. And then in sports, they use mass spectrometer to find the presence of the illegal steroids consumed by the athletes. You can take a sample of urine and check the presence of steroids using mass spectrometer. Likewise, in so many modern users are available in mass spectrometer. But originally, it was discovered for that purpose, to find the relative atomic mass and to find the number of isotopes. So the mass spectrometer has 5 chambers, as you know. The first chamber is known as a vaporization chamber. What does the vaporization chamber do is that it converts the sample into a gas. And this is what you do is you inject the sample over here, and there is high temperature inside this. So that converts the sample into a gas. So remember, if there's a simple monoatomic element, or if it's a diatomic molecule or polyatomic molecule, whether it's a solid, liquid, or gas, it just converts into a gas by high temperature. It is not an atomization chamber. If you introduce chlorine molecule, it will be just as chlorine molecular gas. It will not turn into atoms, right? So this is the vaporization chamber. So then it goes to the next chamber, which is known as the ionization chamber. In the ionization chamber, there is an electron gun which shoots electrons at a very high velocity towards a positive plate. And these electrons knocks the molecule or the atom and removes electron from the molecule. Now, 99.9%, one electron is knocked off from the molecule or the atom, and rarely 2 electrons can be knocked off. Now, here, how the electron is knocked off is this. This is the atom or the molecule, which is the outermost electron, and the electron comes from the electron gun, and comes close to this molecule, there will be repulsion between the two electrons. Now, that repulsive force is greater than this attractive force of the electron towards the nucleus, because both are same electron, but the incoming electron from the electron gun has a very high kinetic energy because it comes at a very high velocity. So when that electron comes close to this electron, there will be repulsion between the two electrons. So as a result, what happens? This electron will remove the other electron because this repulsive force is greater than the attractive force. This is how the ionization is achieved in the ionization chamber. So the electron from the electron gun and the electron from the molecule move towards the positive plate, and that is recycled back into the electron gun. That is the ionization chamber. And next comes the accelerating chamber. There is electric field here, positively and negatively charged plates. And then the positively charged particle, as it enters this chamber, there will be repulsion between the positively charged plate and the positive ion, and that gives some acceleration to the molecule or the atom, and that will move towards the negative plate, and it goes through this tiny slit in a straight line. The particle travels in straight lines in a mass spectrometer because the whole instrument, especially in this region, it's under vacuum, right? Because in a vacuum, there is no air molecule, so the particle travels in straight lines. So the next chamber is the deflector. The accelerated positively charged particle get deflected based on the mass to charge ratio by a huge electromagnet. Deflection is based on the mass to charge ratio. If the mass to charge ratio is greater, deflection will be lesser. That means heavier particles, which has a greater mass, deflect to a lesser degree than the lighter particles. Lighter particles deflect more than the heavier particles, right? Because the deflection is based on the mass to charge ratio, and we know kinetic energy equals half mv squared. If the mass is greater, the kinetic energy will be greater. Mass is greater, the kinetic energy will be greater, right? So particle traveling at a higher kinetic energy, the magnet will not be able to pull that particle much because it's already traveling at a high energy, right? So such particle will deflect to a lesser degree. So then that's the deflector. You have a sensitive screen here. The signal is amplified to a computer where you will see the mass spectrum as a bar chart, right? In the bar chart, the height of it is the percentage abundance, and then the number of peaks in atomic spectra is correspond to the number of isotopes, right? Number of isotopes. So this is signals amplified to a computer and a bar graph. Of course, in 1818, there was no computers. At that time, there's a different technique. Aston used a very sensitive screen, a pre-calibrated screen. From that, a different technique identified the particle. This is the basic of the mass spectrometer, right? So this we have discussed in earlier on the unit 1 as well. Just gave you a quick understanding of it, and then let's see what happens when a molecule is introduced to the mass spectrometer. Now, as I mentioned, when a molecule is introduced, what happens? It turns into a gas in the vaporization chamber by high temperature, and it goes in the ionization chamber. What happens there is an electron or 2 electrons are knocked off. Usually we take as 1 electron knocked off, therefore the charge is always +1. Very rarely the 2 plus is formed. In that case, they will mention in the question 2 electrons are removed. So now, if a molecule is introduced, what happens? A molecule, an electron is knocked off from a molecule. This results in a molecule ion. This results in a molecule ion, right? So this molecule ion, which is formed in the ionization chamber, is unstable. And some of it breaks down into atomic ion and the free radical, which means, for example, if you have a chlorine molecule, electron from the electron gun bombards the chlorine molecule and forms chlorine molecule ion. And this chlorine molecule ion is unstable. It breaks down into atomic ion and the free radical. This is a free radical. This dot represents the unpaired electron of chlorine, right? And this is breaking down of the molecule ion. In fact, most of the molecule ion may break down. Sometimes less molecule ions break down. But some of the molecule ions, before it undergoes this is known as fragmentation, as you have heard before. The breaking down of the molecule ion into atomic ion and free radical is referred to as fragmentation. So the fragmentation occurs because the molecule ion is unstable. But some of the molecule ions, before it undergoes fragmentation, it is deflected and detected, accelerated, deflected, detected, because it is some of the molecule ions, before it undergoes even fragmentation, it is accelerated, deflected, and detected, right? So that gives a molecule in the mass spectrum a bit complicated series of peaks. Right? For example, if I am to draw the mass spectrum of chlorine, so this is always in the mass spectrum. The x-axis is the mass to charge ratio, and this is percentage abundance. So chlorine breaks down into Cl plus and chlorine free radicals. So there are two possibilities for Cl. You have Cl 35 plus and chlorine 37 plus. So therefore, you get a line peak at chlorine 35 and 37. And you notice the 37 peak is about 1/3 of the 35, sorry, 1/4 of the 35 peaks, because we know chlorine 37 is about 75 and this is about 25%. This percentage abundance of chlorine you need to remember. And as for the molecule ion, the molecules which does not undergo fragmentation, that is accelerated, deflected, and detected. So there are three possibilities for molecule ions here. So you have chlorine 35 combined is chlorine 35, resulting chlorine 70 plus molecule ion. You get a peak at 70. And you can combine chlorine 37 with chlorine 35. You get a peak at chlorine 72 plus, quite shorter than 70 because 37 is less percentage. And then you got at last 37 combining 37, you get chlorine 74 plus. That will be a tiny peak at this point. So now in the mass spectrum of chlorine, you have these 5 peaks. That doesn't mean chlorine has 5 isotopes. It has only 2 isotopes. If you want to count the number of isotopes in diatomic molecule, you have to count the number of peaks at the molecular atomic ion region, this region. So this 70 is labeled as M plus peak. That is a molecular ion peak. Right. As for 72, the next one is 72 here. That is M plus 2 peak, and 74 is M plus 4 peak. What is M plus 2 means? That is, M is a molecular ion. Plus 2 means 2 units next to the molecular ion. You can see a molecular ion is 70, right? So plus 2 is 72, right? And plus 4 is 4 units next to the molecular ion, which is 74. Got it? So chlorine mass spectrum looks like this. And the tallest peak is called the base peak. That's the most stable peak, right? In fact, for the base peak, we give the relative percentage abundance is 100%, and all the heights of the other peaks are measured with respect to that peak, with respect to the base peak. All right, clear? So I explained about the fragmentation, about molecular ion. Free radical is a neutral atom, and why we assign a relative abundance of 100 for the base peak. And before I explain about the nature of fragmentation, I'll explain that shortly. You can copy this here for question 4, the mass spectrum of chlorine. In this given space here on question 4, please copy this. Right, so let's see when it comes to a complex organic molecule, how the fragmentation occurs. Now, fragmentation gives always a positively charged ion and a free radical. When it comes to organic molecule, the carbon-containing molecule, this positively charged ion is referred to as a carbocation. So we know the stability of carbocations. The tertiary carbocations are more stable than the secondary carbocation, and secondary carbocations are more stable than the primary, right? So therefore, the fragmentation always results in a more stable carbocation. So there is an option, say for example, you have option of forming, you say you have a molecule of option of forming a secondary or a primary carbocation, then you have to select a secondary carbocation because it's more stable, right? So fragmentation occurs so that it results in a more stable carbocation. So tertiary carbocation, we know it's more stable than secondary, and we know secondary carbocation is more stable than primary, right? Yeah, so always, if it comes to the complex organic molecules, fragmentation occurs so that it results in more stable carbocation. So each fragmentation results in a positively charged molecule ion and a radical or sometimes a stable molecule such as water, hydrogen, or